got a sample AP problem here from the AP exam, and it may be important for you to go on the website and get a copy of this for yourself, depending on how well the print actually comes through the video. We'll make sure to read the questions out so you can just follow along, but it would be helpful to have a copy of this in front of you. A 50-kilogram cart moves on a straight horizontal track. The graph of the velocity versus time is given below. So we've got a velocity versus time graph here. Indicate every time for which the cart is at rest. Well, when an object's at rest, the velocity, the instantaneous velocity, is equal to 0. Now, since this is a velocity graph, we want the places where the instantaneous velocity is 0. So here's one here at t equals 4 seconds. And the only other place where the velocity equals 0 is that location there at t equals 18 seconds. Don't be fooled into thinking that the flat parts are at rest, because this isn't a distance graph. What's happening here is that the object is changing direction at these points. Even though you have a steady slope, remember that slope means acceleration, not the actual velocity of it. Indicate every time interval for which the speed is increasing. Well, notice that it just says the magnitude of the velocity. If we look at this first segment, what we can see here is that the speed is decreasing. The number is getting lower. You're going from 0.8 all the way down to 0. But then you stop. What we've got to realize here is that a transition has occurred. We've changed direction. And now the numbers are increasing in the negative direction. So from t equals 4 seconds to t equals 9 seconds, we're gaining speed in the negative direction. Don't be fooled by this little section right here. This little section here, the object is actually slowing down in speed. From here all the way to here, the numbers of the velocity are getting smaller. Our numbers start increasing again at t equals 18 seconds, and we get faster all the way up to t equals 20 seconds. Once again, speed is just how fast you're going. It doesn't matter what direction the object is traveling in. So during the sections we indicated on the graph here, that's when the numbers, or the magnitude or the velocity, is getting higher. Part C says, determine the horizontal position of the cart at t equals 9 seconds if the cart is located at x equals 2 at t equals 0. So in the beginning, the cart was on the 2-meter line. And we want to know what meter line is it on, if we kind of use a football analogy, what meter line is it on at the 9-second mark? Well, again, we've got to make sure that we interpret this velocity graph correctly. Remember that since we're dealing with position and we've got a velocity graph here, we want to look at the area underneath the graph. We've got some area right here, and then we've got some area right there. So we've got two different areas to consider from 0 to 9 seconds. Notice that one of these areas is over the x-axis and one of these areas is under the x-axis. Right away, that tells us that we've got two different directions to deal with. This is going to be a positive displacement, and this area is going to be a negative displacement. Let's find the actual areas and then we can talk about what to do with them. We've got 0.8. Since they're triangles, we use 1/2 base times height here. So we'll do 1/2 times 0.8 times the base here, which is 4. So that would be 2 times 0.8, or 1.6 meters. Put a little box around that. And then over here, we've got a base of 1, 2, 3, 4, 5. 1/2 times 5. And then the height is 1. So this is going to be a displacement of negative 2.5 meters. We're below the axis here, so this has been a negative velocity, so you're going to have a displacement in the negative direction. So if we start at the 2 meter line, come down here and even draw a diagram of this now. Here's 0 right here. We start at the 2 meter line. The first segment said we went forward 1.6 meters. And so that's going to put us on the 3.6 meter line. But then we've got to turn around and go back the opposite direction, 2.5 meters. 3.6 minus 2.5 is going to be 1.1. So the answer to our question is the new location of the cart after this motion is going to be at x equals 1.1 meters. Again, that's because we had some positive forward motion and then we had some negative backward motion. Again, that's assuming a standard frame of reference where forwards is positive and backwards negative. And if you look at the story here, it sounds like a reasonable assumption to make. We've got one more question we want to look at. We're asked to sketch an acceleration graph for the entire interval. Well, we're going to have to flip back and forth here, and this is where it's going to really help you to have your own copy. Remember that the acceleration is going to be the slope of the velocity graph. So what we've got to do is we've got to look at the slope for each of these sections. And so we've got one section with constant slope going all the way up to 9 seconds. So I'm just going to put some little dots on here to remind me of the sections. And right away, the sections that are horizontal, the slope equals 0, so I can go ahead and put that on here. My next section here is going to be from 9 to 12 seconds. So let me put a little dot at the 12-second mark. I've got 0 slope from 12 all the way to 17 seconds. And then my next segment goes from 17 to 20 seconds. And then from 20 to 25 seconds, I've got 0 slope here. I'm going to go ahead and mark the locations where there's 0 slope. For the first 9 seconds, I have a constant slope, and it's a negative slope because our graph is going downhill here. That direction is going to be a negative slope. an easy place to look at the rise over run would be 0.8 over 1, 2, 3, 4 seconds. So if I come up here and say rise over run, my rise is actually negative 0.8 over 4, which equals negative 0.2 meters per second squared if you do the standard units of acceleration. And that's constant. So all I need is a nice steady line for the first 9 seconds at 0.2. In this section, my rise over run, my rise goes from -1 to -4. So that's a rise of positive 0.6. So that's instead of a fall, that's a rise. So that's going to be a positive rise. My run is 1, 2, 3. 0.6 over 3 is going to be positive 0.2. Notice how we have a sharp point here. So we're not going to have a smooth transition. We're just going to jump up here. We're going to have a quick jump, an instant transition to positive 0.2, and then an instant transition. Again, you notice how there's no curves in here, so we don't have smooth transitions between different accelerations and different slopes. We're going to make sharp transitions. But that just leaves us one more section to actually find the slope for. Again, you don't have to find the whole thing because it's a constant slope. You can just use the easy to read points. So we go from 0 all the way up to 0.8 again. So our rise, and this is since we're going upwards, this is a positive slope, 0.8, and we accomplish this because I'm only using a partial section. This rise of 0.8 happens over 1 to 2 seconds. I knew it shouldn't have been that hard. Our rise is 0.8. Our run is 1, 2 seconds. So that's an acceleration of 0.4 meters per second squared. And so our final section of the graph is going to be up here at 0.4. Again, instant transitions. And so we've used our relationships of slope and area to analyze a motion graph to be able to talk about what's happening to the measurements of displacement, velocity, and acceleration of an object over a period of time.